Stellenbosch.
Okay, great. Thank you, Prof. Okay, so today's session we're going to start with is computational thinking. And this is going to be by Prof. Francesco Petriccioni. Prof is a professor of quantum computing and director of the National Institute for Theoretical and Computational Sciences, so NITheCS, at Stellenbosch University. He was trained in physics at the University of Freiburg, where he obtained his PhD. He has held senior academic and leadership positions in Germany and South Africa, including Professor of Theoretical Physics and Pro-Vice Chancellor of Big Data and Informatics at the University of KwaZulu-Natal. He is a South African Research Chair in Quantum Information Processing and Communication, a fellow of several leading scientific academies, and has authored over 250 peer-reviewed publications, including influential works on quantum systems and quantum machine learning. And Prof will be assisted by Ms. Deepika, who is a geoinformatics computer science student at Stellenbosch University, who will be focusing on the hands-on coding session of computational thinking. So over to you, Prof. and Deepika.
Yeah, thank you very much, Krishna. I think at some stage I will have to send you an updated biography. Okay, let's start. So the idea today is to, I hope you can see the slide, to give a very short introduction to computational thinking. Yeah, if I manage to change the slides. Okay, thank you. Thank you. So this is the plan. So we divided the day in 4 sessions. Yeah, one now to the coffee break, from the coffee break to lunch, and then from lunch to coffee break, and then until just 4. Yeah, and each session we decided with Deepika, I will give you a little overview. Yeah, and then we will go straight into the program. Yeah. So Deepika will show you then maybe the rough skeleton of what's to be done, and you will have some time to do it, and we will be here to assess if there is any challenge. Yeah, so the plan in the first section is now to maybe briefly tell you what computational thinking is about, a very, very, very short history of how we got here. Yeah, and then I will explain the 4 pillars of computational thinking, which are very important because it's something that one should always keep in the back of the head every time you start programming something. Yeah, we will do a very simple example, and so I think this I swapped. It was supposed to be the other way around, but we will see that as we go. So the term computational thinking, yeah, is relatively new. This lady wrote a very influential paper, and in the lecture notes that we will give you later, there is a reference, and coined the term. Yeah? So the idea is to have a really systematic approach to problem solving. Yeah? And the idea is to really formulate problem in such a way that a computer can solve. Yeah? And I think in the year 2026, I think it should be knowledge of every STEM and even non-STEM student, yeah, or academic. Yeah? Because in the meantime, even the humanities, and we have an example just now, yeah, make it extensive use of this computational tools. Yeah. So, the story of algorithms goes back the 9th century, yeah, where this Iranian mathematician, yeah, whose name sort of remembered algorithm, yeah, and maybe Omid, who is from Iran, maybe know how to pronounce it properly, yeah. And and he was just trying to create an algorithm to solve linear equations, quadratic equations, very simple things. Yeah, and he did such a good job that his surname became algorithm. Yeah, that we use every day. And the book that he wrote, yeah, again, we might be able to pronounce very is the origin of the word algebra, yeah, because he was trying to solve simple algebraic problems. Yeah? That is more than 1,000 years ago. Yeah, so some of us are still struggling with it. Yeah, but let's make a jump to the last century. Yeah, there really there are probably you can pick up as many highlights as possible. Yeah, but two really fundamental ones was Alan Turing, that you probably know from the famous movie. Yeah, British mathematician. Yeah, was involved in deciphering the secret codes of the bad guys during World War II. Yeah, but he wrote in 1936, just before the Second World War started, a very important work on what is now called the Turing machine. Yeah, and he sort of abstracted the principle of a general machine that does any kind of computation. Yeah, and and that was very important for computer science and and for all of us. More recently, maybe 50 years later, this gentleman, Donald Knuth, yeah, and some of you might know him because he invented latex as well. Yeah, he programmed latex that has been used to do this slide. Yeah? But he wrote, I think it's 4, 5, or even more books in the meantime called The Art of Computer Programming. Yeah? And that's essentially the Bible of computational thinking. Yeah? There is a volume on every kind of pillar of computational thinking. One book on random processes is really very, very, very famous. Okay, so if you're looking for an algorithm, look it up. Yeah, you should find it in there. Very nicely. I think it is. I'm not sorry, I got the colors a little wrong. So what are the 4 pillars? And we will discuss them just now. Sorry, here something went wrong. Yes. There is decomposition, pattern recognition, abstraction, and algorithmic design. Yeah? So these are kind of the recurring themes of everything you do when you start coding. It might sound now all abstract, yeah? But the more complex the problem gets, the more important it becomes to think about these things. Yeah? And I think I have here a very simple example. Yeah, let's assume you have 1,000 books, and at random, you need to put them in bookshelf in some ordered way. So what do? The first thing is you remove all the books, you put them somewhere on the floor, and you try to categorize them in files. Yeah? And then you put them back on the shelf. Yeah, this will be the composition. Yeah? The pattern recognition will be, you look, some books are physics, some books are computer science, some books are novels. Yeah? You sort of group them. Yeah? Some people could say, okay, I want tall books here, there's more the paperback somewhere else. Yeah? That is a matter of taste. Yeah? But more importantly, you could also recognize series. Yeah? Harry Potter, 1, 2, 3, 4, 5. Then you need to put them together. Yeah? And that comes the abstraction. Yeah? There are things that you ignore. Yeah? For instance, how much does the book weigh? Yeah? It doesn't really matter if you want to put them on your bookshelf. How many pages does it have? Yeah? Yeah. So you want to focus only on let's say, on the last name of the author. Yeah, that's the important length. Yeah. And then you start with the algorithmic design. Yeah, you pick a book, you look at the first letter of the surname of the author, you put it somewhere, and the next one you put it in front. Yeah, that would be very primitive sorting algorithm, and then some kind of do loop until all books are off the floor. Yeah? So if you do a playlist, how does it work? I use Spotify, but it could be Apple Music, whatever you use. So next time you
My audience sold by so many.
you create a Spotify or Miracle Music list. Yeah, you think about this. Yeah, and yeah. So let's go quickly through all the four pillars. Yeah. So the composition is really you want to decompose a complex problem in chunks, in simpler problems that you can solve one by one. Yeah? You want problems that are manageable. Yeah? For instance, if you were to build a car, yeah? You don't start building a car. Yeah? You need first to build an engine, then you need a chassis, you need electrical system, you need steering wheel, you need lights, you need, yeah? So these will be the basic component that you can further decompose in more elementary. So the engine is made of many parts. Yeah? Sorry, sorry, I can do fast. Yeah. So next pillar is pattern recognition. Yeah? And this is the skill of identifying similarity, trends, regularities. Yeah? Again, in problems and sub-problems. An example that we will code later, before the coffee break. Yeah? You want to analyze a text. Yeah? So one gives you a file of a text. Yeah? Could be the lecture notes of today. Yeah. We come to you later. Yeah? And you could see, are there patterns in the words? Are the words that come over and over again? Are the sequences of words that are repeated in the text? Yeah? And do you want to count the words, the sentences, the syllables, and so on and so forth? Yeah? And then you can apply the same logic to all levels, yeah? From words to sentences, paragraph, section, subsection, chapters, and so on and so forth. Okay. So this is very important. Yeah, but of course, pattern recognition, you can use it in many other areas as well. Yeah? Okay, abstraction. Yeah? Abstraction is very important, yeah? Because it's the pillar that forces you to focus on the essential. Yeah? Sometimes you need to model the forest, but not every single tree. Yeah? Or for instance, if you want a map of Stellenbosch, you don't want on the map the color of every building. Yeah? You go from here to, I don't know, to Dorp Street. The color of the building is fairly relevant. Yeah? Something like that. Yeah, or if you think of, if you've been to, I don't know, to London, everybody knows the subway map. Yeah? It's very abstracted. It's not exactly how the trains go. Yeah, it's just an overall distorted geography, just to have the clarity of the map. Yeah? So the algorithmic design. Yeah, and this is also something that we will do just now. Yeah? You want step-by-step instructions. Yeah? And for instance, a very simple algorithm, yeah, is you want to approximate fun. Yeah? And there is this famous formula, also goes back 200 years. Yeah? Yeah? And you recognize sort of the pattern. Yeah? 1, 3, 5, 7, and so on and so forth. Yeah? The sign alternates. Yeah? So you can code it very efficiently. Yeah? And this will be the first thing that we do. Yeah? And and the idea is that this converts, but it doesn't convert very quick. It's not a very fancy forward stage one. Maybe when you code it, you can try how many iterations, how many sums, turns in the sum do you need to reach 5 with 5 correct digits. How many do you think you need?
15. I would say 15, between 10 and 20.
15. Who offers more? 50. 50. Who offers more?
500.
500, 12 us more.
Yo.
You will be surprised. You need 100,000. Yeah,
Wow.
more or less. Yeah, but that's what we will do. Yeah, and there are other methods to do it much more efficiently. Yeah, but it just to get an idea how you have a very nice step-by-step solution, but maybe it's not the optimal. Maybe it's not the optimal one. Yeah, so we will see it how it goes. Yeah. Okay, one of the examples that we will look at just now, yeah, is text analysis. Yeah, Deepika will give you a text, yeah, and you can count the sentences, you can count the words, you can count the characters, yeah. You can try to find the unique words, yeah, and all this can be put together. I don't remember if I have it now here. Yes, yeah. In this famous formula, yeah, Flash-Kincaid probability test, yeah, which is an empirical formula to see how readable a text is. Yeah, is it a text that 5-year-olds can read? Is it a text that requires a PhD in Latin? Yeah, or something like that. This is quite a funny formula. Yeah, there is some constant, the ratio of words, total words to total sentences, the ratio of syllabes to words, and it gives you a number, a score that tells you is the text readable or is the text very different. Yeah? And yeah, and we will try to play with it later. Yeah, so that you need to learn how to do a few a few things. Yeah? Okay. Sorry, but I think I put that slide in the wrong place. Okay, so again, back to pi. Yeah. So we want to use this famous formula. Yeah. So what do? Yeah. First we decompose. Now we need to start some. Yeah. We need a variable to store the sum. Yeah. Then we need to iterate n times. Yeah. And in the loop, we need to start from the term that we have and add or subtract whatever from the sum. Yeah? And at the end, you multiply by 4. Yeah? So not so difficult. Yeah? And here you see, you can make use, it's a very trivial example, yeah? But I just want you to think about the 4 steps, the 4 pillars. Yeah? The pattern recognition. Yeah? You recognize either 1, 3, 5, 7, and so forth. Yeah, and this is the iteration formula. Yeah, the sign alternates. Yeah, plus minus, plus minus, plus minus, plus minus, and so on and so forth. Yeah, so that used to extract the formula, abstract the formula for the term that you had at every step. Yeah, and for instance, a simple program could be something like this. Yeah? And what I mentioned before that I would like you to play around is, the variable that you have is the number of terms. Let's call it n terms. Yeah. Try with 10, 100,000, yeah, and see if you get 3.1415 and so on and so forth. Yeah. And you will see to get 5, 6 digits right, you need really many 100,000 of terms. That is the tier. Yeah. Okay, so I even wrote it down. So it takes around 100,000 terms. That is something. Okay, yeah. So the reason why I mentioned this is that you can come up with a fancy algorithm, yeah, but you need to check the quality and the efficiency of the algorithm. Yeah, it might lead to the solution, but having 100,000 terms for 3, 4 digits is not exactly practical. Yeah. So just because an algorithm works doesn't mean it's the best. Yeah. So there is always in practical life. Yeah? Once you have an algorithm, it's good. At least you know there is a solution. Yeah? But most of the time, it doesn't end there. Yeah. You need to look Can I optimize it? Can I change the order of the loops? Can I, is there a better algorithm? Having something that works is always good, but usually it's not the end of the road. Yeah? Another thing that you could, I don't think we will do it today, yeah, but you could try to build a spam detector. Yeah? Before you start coding, you have to think what you do. Yeah? So the first step is again the composition. Yeah? So how do you analyze the email that you receive in your inbox? You just look at the sender. You just look at the subject. You want to analyze the body. Yeah? You want to check the attachments. Yeah? Yeah? Then you could say, all spam emails have some patterns. Yeah? Someone could be the sender is General so and so from Nigeria, that wants to send you $1 million for whatever. Yeah, that's a pattern. Yeah? Because each of you have probably received 100 emails along those lines, yeah? And so on and so forth. Yeah, and then abstraction. We care about the color of the fonts, yeah, and so on and so forth. I think that we want to ignore. Yeah. So for every problem, this is just a random example. Yeah, before you start with your Python code, yeah, think about these steps. I think I forgot one here. Okay. So just to summarize a little bit now, yeah. Computational thinking is really important, yeah, and people realized it not so long ago, yeah, and follows a long history, yeah, that started more than 1,000 years ago, yeah. Again, these are the four tools that we need to think about. The first step: the composition, pattern recognition, abstraction, and algorithm design. Yeah? And every problem, as complex as it can be, always think about that. So now we have. So my plan was half an hour. I was a little bit faster, but now we have 1 hour, yeah, or more or less, yeah, until the coffee break. To do two things. One is just do the pi thing, yeah, the pi approximation, yeah, and maybe think about a better way of doing it. Yeah? There are also, you can calculate pi also with Monte Carlo net. Have you done that already? Yeah. Imagine a circle in a square of, let's say, of side length 1. Yeah. You throw random numbers. Yeah. And you look at the ratio. Does it fall in the circle or outside? Yeah. That's also a way to approximate the pi, because the surface of the circle is pi r squared. So it's pi if r is 1. Yeah? And the circle of the square, as well. Yeah? How many iterations do you need there to get 5 digits right? I don't know. You can find out. Yeah? And maybe there are other ways to do that. Yeah? So that should be a simple exercise. Yeah? A little more challenging is maybe the text analysis. Yeah? Those are the two things that we do in this section. Yeah? And there, I would say, try the pi thing on starting on your own. Yeah? And then, it's very simple. Yeah? And the text analysis, Deepika will give you maybe a few hints and maybe the same text, so that we're all on the same page. Any questions? Please.
So on the pi problem, is there also a pattern recognition and an abstraction step?
Yes, because if you look at the series, in the denominator there is 1, 3, 5, 7, 9, 11, and so on and so forth. Yeah? And then the sign, plus, minus, plus, minus, plus, minus. Yeah? So, that's a very simple example. Yeah? But, sometimes I always like simple examples because you really see it. Yeah, and it's nice to imagine. Yeah? Would you like to give it a try? Krishna, is everybody giving it a try? No. Sorry? Yeah. Yeah, we can leave it there. Yeah. Is there any feedback from all the? I couldn't look this up. Krishna, can you still hear us?
Yes, Prof. Again. Sorry,
Yes, yes.
Okay. Then let's give everybody 10-15 minutes to do the fighting, and then we start the text analysis together again. Yeah.
Okay, sure, no problem.
And maybe after the session, we put the slides in Canvas, and not before. And we also have a set of lecture notes that we'll upload as well. Some people asked in Slack. Yeah.
Prof, maybe you can show the complete formula, not just this one.
Yeah. Yeah, we go.
Much better.
Yeah, so the only variable that you have is the number of terms. Yeah. And then you can tell me how precise it is. What was the guesses? 10, 15, 50, 500. Yeah. Let's see how it goes. And we have to fill the code that we have the model solution we can put on this just one time after. I don't know. It's not good. That speech on another one. It's good. Yeah, just using the five across with They're not allowed to check the PTS. Everyone's kind of going to be using it. I think
Yeah, perfect.
Let's see. The people is not up with this. This is it's like channel. Whatever you do, it's like clear it could not be out.
Or in Slack, somebody asked what we're exactly supposed to do. Maybe we're supposed to program in Python with approximation formula. Yeah. Or whatever system you like. Right? And and the only variable that we should leave open is the number of terms. Yeah. So that you can see how good it converges if you sum 10 terms, 100 terms, 1,000 terms, 10,000 terms, so on and so forth. And it shouldn't be too difficult. I hope. No, don't use ChatGPT. Or Claude or whatever.
Or Grok. Probably.
Or Open Claude. Maybe the first one who has it can shout up, and then we can share the solution and go through it. Everybody can then get it their own time. We are going very well with time. Progress.
I've not yet. It's just logging in. This is Zoom. Yeah, I still use this for later for the day. Oh, this morning.
Just take a screenshot because
Exactly. Yeah.
Benjamin mentioned if you're going to put a screenshot.
I'm supposed to code
But
this.
this on Slack, I don't know, maybe some people haven't. Benjamin mentioned. Can you take a snapshot of the screen? It's easy, just.
Yeah.
Screenshot. It's all together.
Excellent.
exercise. Yeah.
Was it right?
Yeah, I've seen
So what I just used Google Colab using the tools I could develop. So okay, they just didn't have money and the forms open it to Google based on they click and it runs on a cloud. Or is maybe the one that gives you the solution immediately. You can ask about Google Colab. You can even do visualizations as well.
But what would you do for something else asking about me?
So the area is the difference between
I don't know, the sound from you. There's a factor of four missing somewhere.
He's on organized instead of the on
Some is I over 4. So okay, and do you have any winners? Does 3.1415 come out? Well,
I was approximately 5 or 4, so I wasn't.
okay, but let's approximate pi because I know how pi starts, but I don't know how pi over 4 starts. Yeah. Then we can have you played with the
3.14 to 1.5.
okay, with how many iterations?
It's
Million, 7. Okay, perfect. Then I don't know. Do you want to go through the?
Yeah.
I'm sorry.
yeah, a solution.
All right.
You make
Morning,
this.
everyone. So just walking around the room, we have some people that have already figured it out, but I guess we can go through it together. The general census is that everyone's using Anaconda, which is perfectly fine. But I also have a Google Colab workbook, Jupyter notebook that we can all work on together. Just uploaded it onto Slack. And it will serve as a template for the rest of the exercises we will do today. Because some exercises will be a little bit more challenging, and it just helps to have that templates that will guide you through the coding examples. So I've uploaded the. Right now we'll be doing the code along. I will help you code the approximating pi code. I uploaded the Google Colab, and because this is shared on my drive, please can everyone go to file and make a copy on your own drive so that we are not all working on the same document. That would be lovely. And then if you look in the table of contents, you'll see all of the examples that, sorry. Nobody can see what I'm pointing at here.
And Deepika, maybe you can show how to make a copy exactly.
I will show you. Sorry, I was doing that, but I didn't know it wasn't sharing.
Yeah, that's fine.
There we go. Okay. So now I hope everyone can see my Google Colab notebook, my Jupyter notebook. And to make a copy, you go to File and then save a copy in your drive. And then you redirect it to a new tab. And say making the copy. And there we go. That should be your version. And then we can go to pick on approximate pi. And this is our template. So I just want to get a general idea. How did everyone else do it? Did you make a function or did you just hard code it using the formula? This. You? Oh, how to copy the workbook. So you go to File, and then there should be a Save a Copy in Drive. And that should redirect you to your copy of the notebook. And if you're not logged into Google, you should log into your Google Drive. I can just get a thumbs up to see in general how many people are ready. Yeah? Yeah? Okay. As you can see in our notebook, I put in the formula. So maybe everyone did it in one go, where you just take the -1 to the power of whatever number and use the loop, hopefully, to get the different terms, a for loop. So first we want to initialize our variables. Because pi is a number with many digits, many floating points, like as we call them, we initialize it to 0.0. So it's not an integer, it has decimal values. Okay. And now we need a loop to actually get how many terms. You see AI wants to complete it for me. So we're going to start with our for loop. You can say for I, and in this case, because prof in our formula says k, we will use k, and it's just a variable that tells us what number we're on in our loop. So we say for k in range, and then we use our number of terms. Because just like formula, the number of terms is where we're going to end. And luckily, we don't have to manually calculate it. If we were doing it on paper, we have to calculate 1, 2, 3, 4. But this for loop will do it all for us in seconds. So we got our loop. And then we want to add our logic into it. So it's a converging series, and we have to alternate the symbol. And we figured out that we can actually use -1 to the power of k to interchange these symbols. So to get the value, we're going to have to say what pi approx is going to be now. So-
Deepika, just sorry, 1 minute. Can you maybe zoom in a bit? It's a little small.
Oh, okay, thank you. I'll do that.
Well, you can also close that part here.
Close this up.
Yeah, because that's relevant.
All right now?
Yeah, that's better. Thank you.
Okay, yeah. Now, because we have to add all the terms on top of each other, we can't just put a simple equal to. Otherwise, it's just going to overwrite itself. So if we do, for example, we start off with 1 minus a third, we're going to be left with 2/3. But then let's say we put equals to, it's just going to keep on changing it to the next value and not actually sum it up. So in order to sum it up, we have to use the plus equal to sign. And then we can start with our -1 to the power of k, with our interchangeable symbol. And then you can either, I don't know if everyone multiplied it by 1 over and then the term number, or you can just divide it by term number. And that's, coding is just mathematics. It doesn't matter how you do it, as long as at the end of the code, the numbers match up. So 2 to the power of k plus 1, just like in our formula above. So now I think everybody got to this part, and then I think maybe we forgot something, yes? Because if I run this now, I'm going to get a 0 point something, because this formula that we just typed out is equating to pi over 4. So we still have to multiply by 4. And to do that, we're just going to say at the end of our for loop, pi approx multiply by 4.
That's what I want to do. Is that?
And then again, this is just a compound formula. Instead of saying pi approx is equal to pi approx times 4, we can make it less redundant and just say multiply equal to 4. Is everyone with me? To the question, why make a function? Can't we do it without a function? Yeah, you can absolutely do it without a function, but then at the end of the day, if you want to somehow apply it somewhere, that's the whole thing we're talking about, decomposition. This pi approximation function could be a part of something bigger. But yeah, of course, you don't have to use a function. Now, to get this lovely looking output in our terminal, we're going to have to code another loop, print this out. And that's partly why I wanted to use a function, because then I can just use multiple values without having to manually go back and change the number of terms each time. So as Prof's question was earlier, how many terms is it going to take to actively approximate pi? So that's why I made an array for a list from 1 to 100,000. You even add 1,000,000. And now we can code a simple loop just so that we can see the value of the approximate of pi for each term. So we're going to say for T our list. And what that means is for a variable, for a number in the list that we have. So that means it will go through each number in our list. we're going to say our value is equal to, and then our function that we use, which is approximate I. And then we use t because that's our increment value in our list. And then just to get it to print out the values in this format. I don't know if you used it in the beginning of the week, but instead of saying the string using plus then your value, let's say t, you can just put it all using the f function, using, and then using curly braces to put in your actual values. For variables that you used in the code. Then what I'm doing now, 6F, is just a formatting so that when we print out, it will actually print out to a certain amount of decimal digits. Just so that it doesn't continue on forever. And even the F stands for floats, because we're using a float for compile approximate. And 6 should be the decimal points. All right, if everyone is happy, we can run our code just by pressing the arrow in the corner. Okay. And when you press the arrow in the corner, it should give you a green tick and your time of how long it took to compile. It takes more than 1 second, you should be worried. And then we can actually compile our main function. Our main function is what we use to run our function. Then you should get the outputs. So we look 1 term should equate to 4. 10 terms is only 3.04, close, but not 3.14. 100 terms, 3.13, almost, relatively. 1,000 is 3.14. And then you can just keep on going. You can just keep on adding numbers to your terms list. We can even add not in units of to the power of 10. You put like 59 or 77. Add to your list and we'll iterate and give you the values. If you want to print just a singular value, you can say, you can just access your function by saying print approximate I, and then of course the term. And it should give it to you. At some point it will overfit. So just play around with it, see how far you can go. Something we love to do in computer science is just see how much we can do before the computer crashes. If the computer crashes, you know you did it right. That's a question of the last 2 months. About the last 2 months. The if name equals main is just, it's an infamous line you'll always use. Do I even know the meaning behind it? No, but we were told since day one, if you end your Python code when you have multiple functions and you have a main function, you end your main function with if main equals main, and then you put main in the indentation and you will run your main code. I hope that explains it. Scripture, it's like the holy rules of computer science.
Is everyone happy now with the warm-up exercise? So I see the time getting bored.
Yeah.
Is everybody happy
Is
with the
everyone happy?
warm-up exercise? Could we use the text analysis one? That might be a nice
Only rule.
challenge.
Yeah.
If you can answer the question about.
Yeah, I think I hope we answered your questions.
It knows where to get it, so you can decide how to.
Another way to run it in the notebook is to close that section and just press the value of resource. When you open it, it should start.
The pi is open, and also there you are called bottom of pi. And
So
you just call the function.
we are nearing our tea break, but we have one more problem. The text analyzer that Prof discussed earlier. Yeah. So
Exactly. So
everybody seems to have warmed up now, have an idea of how to do this. I have the template text analyzer inside of the Jupyter notebook. But as you can see, there's stuff missing. And it's not because I forgot to code it, because I took it out. And I hope that
that's a cool.
everyone enjoys this challenge. As Prof mentioned, there are many things on an everyday basis that we don't think of the computational thinking logic behind it. And we open Google Docs or Word Docs, or everybody loves Grammarly. And we don't realize that it actually uses computational thinking to tell us how many words are there in a text, tell us how many syllables, how to rate our text using that formula. And the computer actually does this just by looking at patterns. Looking at patterns of, is there a space between these two words? Does that mean that allows you to count how many words are in a text? If there's a full stop or exclamation mark, that means the end of a sentence, then we can increment the variable named sentence and keep incrementing until we hit multiple blank spaces. Then we can assume as a computer, oh, this is the end of a paragraph, or this is the end of my text. So what I've done in textanalyzer.py is we have multiple functions. We have the count words function, count sentences function, count paragraphs function. I did the more unusual, even I struggled with this because I had to figure out how do we as humans, counting syllables comes naturally to us. We learned it in primary school, like hello is 2. But computers can't naturally think of this in the same way that we do. So we have to realize, how do we actually split up these words? Hello, or like prof is 1 syllable, or NITheCS is 2 syllables. So you Google it because it's just easier to Google and sit and ponder about a philosophical question for hours. You can see that it's actually separated by our vowels that we use. And of course, this may not work in all cases, but just for our simple text analyzer, it will suffice. So this function is already built for you. So is the count syllables and the calculate readability. As you can see, the readability score is given. It's the same formula we used earlier. This isn't a formula that's used by all text analyzers like Grammarly. They have their in-house secrets, but this is a quite general one. that's been used for a long time. And then once you've done coding these three functions, count words, count sentences, count paragraphs, I have complete faith in everyone to do. And if anyone needs help, just put it on Slack or raise your hand, and I don't mind, but we'll go over it later. Then I'd like you to format it so that when we print our main function, it'll come out in this format. So this analyze text, this function, the only purpose of it is to output, to format these 1, 2, 3, 4, 5, these 5 lines. And preferably you can put it in a dictionary with all of the metrics. I don't know, maybe last week you guys learned how to write a dictionary in Python. Yes? No? Maybe. The dictionary is like the paperbook dictionary. It has a word and then its definition. In this case, our definition will be the actual function's name. So, not to give it away, but let's just say make a dictionary. We just use curly brackets. And we're going to say, AI wants detail. But that's along the lines of what we do. Hopefully, not everyone has AI activated in their notebooks. I hope. But it's not. I hope everybody gives us a good try. And we'll reconvene just before the break to go over the solution. Sounds a little different, but so the sample text, just to make it a little bit interactive, I use the input function. So you can take your favorite text from wherever you can Google, you can write your own text. And all the input will do is allow us to type in or paste or enter our text. If you don't want to input your text, you can take out input and just put in text from somewhere. You use text you're familiar, like Lord of the Rings, maybe last year's lecture notes, maybe these lecture notes when they come out. But yeah, in the meantime, I was just using input. And then taking your response. Please.
Access to the file. AI helps, but we live in the year 2026. And everybody to the AI so it will just helps us stick to the time. Yeah, so I think
Or it's the set as a power would I like it. You always make requirement as well.
let's not visualize self one block at a time. The vision is
You can load your but we need to
solution.
Just to because we using computation in DoD, one of the pillars that we're using in this code is decomposition. So we actually speak about how big a problem of analyzing text each of the different companies. And benefit of using included loading in this case is that we can actually test each function individually. So one of the guys that's done.
All is burned down. So we just unwash. All the net burned down. Burn different ways.
To see if it works. This is the.
It's just a program. Not it's a European program. So it's like a bit
Count the sentences and then people can find to count the paragraphs on their own.
the colors you use filters. Because thousands and the thousands of course. Here's the RGB. So we are going to be to go over the mountains and my vision site. This is one of the see which sound this week.
Yeah.
That was massively
Okay, maybe to start everyone off. Yeah. Start. We can count the words together.
that's that.
So
Yeah, that's
count the words together.
One.
biggest put supplies for I think we use
As you can see, AI really wants to do the whole thing for me, which is lovely, but
it's fine, so it goes all the way.
so let's make a variable called words, where we're going to store how many words are in our paragraph. We can call it count words as suggested, but no.
Simple stuff like I need to know it's already not really this is expecting us to have first can that level of the design self-developing.
And to give our words a value, we realize we have to actually split the text, like I mentioned before, into how the computer is going to recognize what a word is. It doesn't know what a word is. The computer only knows ones and zeros and networks. So it's going to look for these white space characters, as we like to call it. And white space characters register as splits. So that's why we're going to use the split operator and say text.split. And what that basically does is just splices your text, and it tells you how many gaps are in your whole text. And then just to return the function, I put len, so we get the length of words. It just means the length of how many words there were found, how many were spliced from the text. And to test that I'm not talking nonsense and that it actually works, and how you can test it, all of your functions work, is we can print count words. We can print our function just to see if it works. And then we have a text holder. So in this case, we will enter a text. Does anyone have a nice quote that you like? Test it. I'm a huge Star Wars fan, so we'll say May the 4th be with you. Let's see if the computer works and knows. Okay. And are we correct? 1, 2, 3, 4, 5, 6. I guess it's working. All right. Since AI seems to be taking over this lecture, keep me employed for today. We will switch over to VS Code or Anaconda after the break.
Okay.
Hopefully nobody has AI installed there as well.
I didn't have AI here, so.
Yeah, if you just click a button like that.
Wait.
If you can
So now you talk to me.
That equals Gemini.
And this one.
Yeah, that's Gemini. And then
But I think
then it starts.
everybody else could have it.
So the visual code you said about this guy.
I know, yeah, we all have this.
Into this one. This one was also.
And I found that inspiring.
As well.
Nobody has code. Because it also has AI. That's lovely.
That's just.
Well, since we have AI, does anyone want to give us the solution for calm sentences?
Mine is not.
Oh, but on a serious note, even though AI can code this for you, it's still an invaluable skill to know how to do it. Because that efficiency is key in the age of AI. AI can code you everything nowadays. It can make you an app. But security and efficiency are key points that will keep you in the industry, will keep you interested, and will always be a problem that AI can't solve.
Software. Yeah, example. Example. Deleted baby. That's perfect fast.
That's kind of what we were doing.
The practice was just more fun than not big stuff. This is.
There's an option that you can disable.
Like the same thing.
Oh, it's over to VS Code, but
Yeah, you can disable this AI assistant. Google Colab. You can show them to disable this. Go to setting and setting AI assistance. Because you already prepare everything, so it's difficult.
Stuff like that.
Let's show them this and
Guys, if you're having a conversation, please mute because it's now kind of confusing for the students. So let's maybe keep to the content for when you're not muted, and then just mute yourself if you're gonna have a conversation quickly, please.
We have a microphone in the room.
We do device code on that other package we can do that exactly here. Yeah, so here's the device code.
I'm gonna try to.
So just a little tip on how to do the count sentences function. The sentences. Can everyone hear me? So sentences, as I put in the comment, sentences usually end with a full stop, a question mark, or an exclamation point. So let's just put that down. Okay, first let's disable. . Let us all disable AI assistants, please. Just to keep our brains working. So to disable our AI in our Jupyter notebook, we're going to go to settings and open our settings. And it should say AI assistant. And then show AI powered inline.
Sorry, can I maybe make a suggestion? Perhaps you could just download that Jupyter notebook of yours and use Jupyter Lab or Anaconda's Jupyter Lab just to open it up there. That way we have no AI issues.
Okay. Well, I switched it off, so hopefully it shouldn't work. But if we still have this issue, I'll definitely transfer it over the break. Thank you, Krishna. Let's see. And there's nothing. We want to create an array that defines what ends a sentence. Because we know, but the computer doesn't know. So what ends a sentence? A full stop. Then to add another element to our array, use a comma. Then we're going to add exclamation mark. Notice that I'm using single quotations to define the elements in the array and not double quotations. And then question marks also define the end of a sentence. And if there's any literature students, English students that know of any other symbols, we can add them to our array. Now that we have this array, we can say the hint is we're going to use a loop and then maybe a counter, a variable that counts. Say for in our text, if the character, or as we like to say in computer science, char is a character. If that symbol, if the char is equal to one of the elements in our array of sentence ending, increment your sum of sentences and then return that, and that should be how many sentences are in your text. So that's the rough logic of how you're going to do it. Love to see you guys implement it. So just to go over slowly again, we're going to have a loop. A loop that says for char in our text, if the char or the character is in our array of sentence ending. So if it matches with that, then increment this variable called sentence count and return that and test your function. Okay, we can go over the solution slowly. So we're going to say for char for our characters in our text, because we define our text as text. We're going to say if our char is in our array sentence endings. Also, this isn't AI, it's just us computer scientists. There's a lot of words to type, so we like this auto completes our variables. It gives us a list of our variables. Yeah. So if our character is in our sentence endings, then we want to say, that means it's one sentence. We will make a variable called total sentences. And then we're going to increment that by 1. And then to complete the function, we're going to return total sentences. Yeah, indentation is a pain. There we go. So just make sure everything's indented properly. Hopefully it works, and you'll get a return of 2, because it's 2 sentences. The cat sat on the mat. That is Schrodinger's cat. Okay. Count the paragraphs, it's similar to counting words, because we have to just count blank lines instead of white spaces. And a blank line is usually encoded with the character /n. That usually means a blank line. And to be safe for a paragraph, we're going to assume it's 2 blank lines. We're going to start with our variable paragraphs. And then to do this, we actually want to strip our text. To strip it into its parts and then split it according to this double blank line. That should identify where there are double blank lines in our text, indicating that it is a paragraph. Now, as you can see, for count sentences, we use the long method of 4 character in text if the text is in a sentence ending total sentences increment by 1. So that is correct. It is correct. But there are quicker ways to do that logic instead of having multiple nested loops inside of each other. And a quick way to do that is we just say return, and then we put the length, and then we're putting our loop inside of this, P for P in paragraphs. If P dot strip. And what this function basically do, it's the condensed version of what we did above. It says for P in paragraphs, so for a value in paragraphs. If P dot strip is true, so if it is stripped, then we count how many times there is that n value, and then it'll return the number of paragraphs.
Deepika, can I ask that you pause because we are now officially in break time, so you'll have to continue at 15:15.
No problem. It is break time. We will see each other in 15 minutes. Thank you.
Okay. So are we ready? I see a thumbs up on Slack by one person. Okay, it is now 1:15, so Deepika, I believe you can continue.
Okay, thank you. I hope everyone had a good tea break. So we will continue with our text analyzer code, and then we'll move on to some more theory with Prof. So just before the break, we went over the count paragraphs function, which is the second last function that we have to complete before we can actually run our code. So I hope everyone was able to this is a lovely question on Slack. The time is 9 a.m. Will return as two sentences with the current interpretation. Is it a plausible solution to also check for words such as AM, PM, so prof, etc.? Yes, modern text editors will actually put in those cases. Of course, they'll implement it in a different way, but in our simple text analyzer, we're just looking for the simple ones. But yeah, if you want to, you can put in AM, PM, things with multiple. Now to test our count paragraphs. The important part about coding is make sure you identify problems if there were one to arise. You need to test your code part by part just to make sure that everything's working. And once it comes together, you can see, maybe there was an error earlier on in this function. And we need to go back and fix it. And then we can put in a longer text. And our function works. So a question I had in the break is, does it need to have the /n/n? This is actually called an escape character. And what it does is instead of having to put like a enter, 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 because that will break our print statement, this escape character basically means put in two blank lines. And that is what we're checking for. We're not checking for explicitly /n/n. It's a symbol that means a line, a blank line. And it works. 2 paragraphs. And finally, just to piece everything together, I'm going to take out my yeah. Yeah. Yes. It'll still work. Yeah, it'll still work. It checks for two, because two usually means a paragraph is usually, you know, that white line in between. But what you do is when you write a text, for example, here I'll write in text, you have one sentence. And then if I press enter, which is the next line, that would be your backslash in, and I start writing again, it'll be directly underneath each other. I'll have to put another enter, which is another backslash. Yeah. So that's why it's two and not one. Yeah. One would just mean we used it before to count how many lines. Yeah. So we have our count number of words. We have our count sentences. We have count paragraphs. That all works. Count syllables is correct. Count syllables. Calculate readability. You can see the calculate readability function actually uses the count words, count sentences, and count syllable functions. That's why it's important to just keep track of your text, because at the end of the day, things are within another function, and if there's an error in, let's say, our count words, it's going to carry over into our calculate readability and affect our score. That's why it's just nice to debug after every function. Now we're going over to just the formatting before we print everything out. As I mentioned before, a dictionary was used where I just defined the word count. The sentence count. The paragraph count. And a dictionary, using the comma actually is your next entry. So you can put them next to each other if you want, but just to make it visually easier to read and follow, it's better to put them underneath each other. And then you got syllable count. Syllable. And then what we want to do now is a dictionary, like I mentioned before, traditionally it associates one word with a meaning or definition. So the definition of our word count is by our count words function. And then if you look here we go, count words. Let's remember to put in our text. Our sentence count is by our count sentences function. What's nice is we can just select it and then say our text. Our paragraph count is our count paragraphs. Thank you, Prof. Our syllable count is using the count syllables function. And finally, our readability score is calculated by our calculate readability that also uses the text once more. And then you don't have to use a comma to close it off there. It's closed by the brackets. Then, as you can see, this function that we just wrote is going to be printed, used inside our main function as our results. And then our results are eventually printed. Before we run everything, we just want to save our progress into our notebook. Then we can go to the top of our function and run it. And then we can just take paragraph, I took it from our lecture slides. And there we go. So hopefully everyone got that to work. You can test its limits by going to Google or maybe searching a page from a book, you know, and then inputting it and testing that. I don't know if you want to manually count the words or you can put in a Word doc and then check it against your own text analyzer. Yeah, but that was the exercise and I hope everyone enjoyed it.
Okay. So now that you have the solution, you know more or less how Grammarly works. Yeah, because sometimes in Grammarly you see it tells you difficult, easy, blah blah blah, and it does essentially what we've done here. Yeah. And if you know the formula now, you can prepare your text in such a way that it is easy, difficult, or so on and so forth. Yeah, just play the system. And now we will move on to this, the second lecture. Yeah, and let me. And the basic idea now was to share with you some basic strategies to develop algorithms. Yeah, and we will look into some really simple approaches that again come over and over again. Yeah. So let's start again at a very high level. Yeah? So I call these algorithmic paradigms. Yeah, things a little bit like when you're in the kitchen. Yeah, you are your own cook. You know some basic techniques. You know how to fry. You know how to boil. You know how to saute. You know how to, I don't know, whatever. Yeah. And you put all those things together to cook your dinner. Yeah. The same is true, of course, in computing. Yeah, you want to find the basic building blocks. Yeah? And there are three major paradigms. Yeah? One that is called divide and conquer. Yeah? So you break the problem in smaller pieces, yeah? Ideally independent from each other. Yeah? You solve them one after the other and you put it together. Yeah, that sort of makes sense. Yeah? You divide it in chunks, you solve every chunk, and then you put the solution together. Yeah? The next category are maybe greedy algorithms. Yeah? So that greedy in the sense that, again, you do things step by step, but at every step you choose the best solution. Yeah? And you hope that in that way, choosing the optimal solution after every step, it builds up to the overall optimal solution. Yeah? In the last one that, that I want to briefly discuss is called dynamic programming. Yeah? This is a little bit different from the greedy ones, yeah, because again, you break up in chunks, yeah, hoping to solve sub-problems, but they're not independent from each other. Yeah, so there is some some overlap in the solution. Yeah, and dynamic programming optimizes this so that you want to avoid to solve the same thing repeat more than once. Yeah, and you do it essentially by caching, by storing intermediate steps that you want to pick up again later. Yeah. Again, just very high level classification. Yeah? Divide and conquer. Yeah, greedy and dynamic programming. Yeah, in sort of order of of complexity. Yeah, and let's start maybe with a very simple very simple problem. Yeah, let's assume you have a list. Yeah, think of telephone book. Yeah, ordered alphabetically. Yeah, if I give you or unordered. Yeah, if I give you a phone number. Yeah, and you need to find it in the telephone book. What do you do? Yeah. In this case, you just look up every number one after another. If you are unlucky, yeah, the number you're looking for is the last one. Yeah. If you're lucky, it's the first one. Yeah. So on average, if there are n numbers in the telephone book, you need n½ searches. Yeah. On average. Yeah. So this is a problem that is sort of linear. Yeah. Because the complexity increases proportional to the number of entries. Yeah. The longer your telephone book, the longer it takes to find a number. Yeah. In some cases, for instance, if your list is sorted, yeah, there are algorithms. There's one algorithm that we will program just now, yeah, called binary search. Yeah. And that manages to reduce the dependence, the linear dependence to a logarithmic dependence. Yeah. So it's much faster. Yeah. And the idea there is that at every step you reduce by a factor of 2 the number of entries in which you are actually searching. Yeah. So essentially, if you do this binary search, if you have 1 million items, yeah, here it takes you 1 million seconds. Yeah. But with this algorithm, it would take you 20 seconds. Yeah, if each search is 1 second. Yeah, so it's really way more efficient. Yeah. How does it work? Yeah, is it just a very simple example? Yeah, we want to find 72. Yeah. So how do we do it? We first we split it in 2. Yeah. If this number is the number we are looking for, we are done. Yeah. Unfortunately, we are not. But we know because they are ordered that it can't be here. Yeah. Then we split it again in 2. Yeah. If it was here, we would be done. Unfortunately, it's not. So we discard half of them again. Yeah. And if we do it a third times, we are lucky. Yeah. So instead of doing it on average 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5 times, we have it in 3. Yeah? And of course, if you scale it up, the logarithmic kicks in. Yeah? So this is the basic idea of binary search. Yeah? And one of the examples will be to program it. Yeah? So I mentioned here in passing here. Yeah. No, sorry. Yeah, here. Yeah. That the complexity is logarithmic. Yeah. And this, I want to introduce it step by step because it's a really very important thing. Because in algorithm, what you want to know is how the performance of the algorithm is if the scale of the problem increases. Yeah? And it makes a big difference whether it increases linearly or logarithmically. Yeah? And in the case of the binary search, you can see the argument very quickly. Yeah? At every step, yeah, we halve the size. Yeah? So after one step is n over 2, n over 4, n over 8, and so on and so forth. And at the end will be n over n. Yeah? Because it's only power of 2, after k step, we have n over 2 to the power of k. Yeah? And at the end, it's 1. Yeah? So n is 2 to the power of k, and k is then logarithms of n. Yeah? So after logarithms of n steps, we have the solution. Yeah? And this is a simple example in which you can calculate explicitly the complexity of your problem. Yeah? So if you increase the data set size to n, the algorithm takes logarithms of n steps. Yeah. So, and if you take the logarithms basis 2 of 1 million, it's 20. Yeah. So it's really much, much better than the linear search. Yeah. So, and this is one of the algorithms that we will code just now. Yeah. And maybe later we take the screenshot, and that's what that's what you have to do. Yeah. So you start with a sorted list, and we choose some target, and then we start the procedure of halving and so on and so forth until we find the number that we're looking for. Another example that I wanted to mention in this divide and conquer, yeah, is an algorithm called merge sort. Yeah. Yeah. So this is, again, it's it's an algorithm for sorting. Yeah. So again, you have the divide step, yeah, where you split it in two. We've seen that in the binary search. Yeah. And then you have the conquer step, yeah, in which you sort each half. Yeah. So you want to sort a whole list. Yeah. So you split it in half. You sort each half, and then you merge the two sorted halves. Yeah. And here again, you can do, we won't do it now, but essentially what you do is you have the same complexity of the previous one, of the binary search, where we have by 2, plus the complexity of the linear search, because once it's split in half, you sort it out, and that's a linear process. Yeah? So if you put it together, it becomes of the order n times log n. Yeah? If n is the number of data points. Yeah? Yeah. So this is essentially the idea. Yeah. So you start with your list. Yeah. You split it in half. Yeah. 8351, 8351, and 7264. Then you split it in half again. Yeah. And you split it in half again. And then you essentially you do the same upside down. Yeah. You order these two. You order these two, you order these two, you order these two, and then you put them together again until the list is ordered. Yeah. Unfortunately, it didn't fit all on one page. Yeah. But you know what I mean. Yeah. You look at these two numbers and you order them. 3, 8. Here you do 1, 5. 2, 7, 4, 6. Then you merge these two at these steps and you put them in the right order. Yeah. And then you put them again in the right order at the top. Yeah. So this is another famous algorithm, yeah, called merge sort. Yeah. You divide, sort and merge and merge again at the bottom. Yeah? And I think we have also an example of this. Yeah, yeah, we can do them later. Yeah, yeah, perfect. Okay, we will do it just now. Sorry. Yeah, but let me finish the slides first, and then we look at the thank you at the examples. Yeah. So as I mentioned before, you can do the analysis of the complexity of this algorithm in a similar way. Yeah, we have the as I mentioned, you split it. Yeah, and you do the binary search, so that if you put them together, they work in a level that goes with n, and the height of the levels that you put them together, which goes with the logarithm of n. Yeah, so this is an example of n log n. Yeah. Okay, now let's give a look at the third one. Yeah, at dynamic programming. Yeah, and I mentioned before, the idea is again, you decompose. Yeah, but your sub problems overlap. Yeah, so you don't have the luxury of having independent sub problems that you can solve each on its own. Yeah. So we are looking at this case where we have overlapping sub problems. Yeah? And and if we do a recursive solution, we'll have to solve some sub problems repeatedly. Yeah? I'll give you an example just now. Yeah. So the idea behind dynamic programming is that you sort of store the result of certain sub problems so that you don't have to recalculate them again. Yeah. You can put them in some kind of a cache, yeah? or something like that. Yeah, and a typical example, and that we will do. Yeah, we have lots of possibility. Yeah, is the calculation of the Fibonacci sequence. Yeah, so the definition of the Fibonacci sequence, if f0 is one, if 0, f1 is 1, you keep adding and you create a sequence of numbers. Such as 0, 1, 1, 2, 3, 2 plus 3, da, 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 da. Yeah. So what would be the naive way of doing it? Yeah, you start with 1 and 2. You add them and you get the Fibonacci 3. Yeah, but then to come to 4, you need to add 2 and 3. Yeah, and you see there is again 2 is here again. Yeah, and and if you want to calculate 5, you need to add F4 and F3. But to calculate F3, you need F2 and F1. Yeah, so it becomes very quickly complicated, and it goes with 2 to the power of n. Yeah, yeah. So it's way cleverer to you do 1 and 2 to calculate 3. You save 2. Yeah, so you can calculate easy 4, and then you save 3, and you can calculate easy 5. Yeah. So this is a very trivial example of of dynamic programming. Yeah, and I don't want to do the analysis now, yeah? But this goes with n, and this went with 2 to the power of n. And 2 to the power of n is exponential. Yeah? It goes very, very fast. Yeah? So the complexity increases very quickly by increasing the number of iterations. And here it's only linear. Yeah? So, and this is probably the example that we should try to code later. Yeah? Now, another very nice example of the greedy algorithms, yeah, is the following one. Think that you have coins, yeah, like in South Africa we have 1 rand, 2 rand, 5 rand, 10 rand note, 20 rand note, yeah, and you have to pay. I don't know. Did I put? Okay. 26 rand, yeah? What is the minimum number of coins and notes that you can use to pay that amount? Yeah? Okay, here in the example, I have a coin with denomination 1, 1 with 3, and 1 with 4, yeah? and we want to pay 6. Yeah. So one strategy could be take the largest coin, yeah, but then you have 2 left. Yeah, 6 minus 4 is 2. So then you need 2 1 coins. Yeah, that gives you 3 coins. Yeah. But the optimal choice is, of course, to ignore the 4 and just give 2 3s. Yeah, then you need 2 coins. Yeah. So the problem is now, can we create an algorithm that works? Yeah. And what you see here is that the greedy algorithm in this case wouldn't work, because the greedy algorithm in the first step chooses what goes closer to the solution. Yeah? But in this case, it doesn't work because it would choose 4, but then you need 2 1 whatever currency coins, yeah? Which makes it 3. The optimal solution is, of course, you take 2 3 whatever currency it is coins, yeah? To reach your 6. Yeah? So, and this is another beautiful example of dynamic programming. Yeah? So here again is the problem now with more realistic coins, 1, 5, 10, 25, yeah, for instance. Yeah? So how do we do it? Yeah? We want to calculate the minimum coins for a certain amount, and we have these denominations 1, 5, 10, 25. Yeah? So what is that number? Yeah? It's the minimum, yeah, of C with A minus D. Yeah, D is then the denomination. Yeah, yeah. So we can use it solve it in a bottom-up approach. Let me see. Let me try to show it to you here again with our example of 1, 3, and 4. Yeah. So we want the 6. Yeah. Again, we want to find the 6. Yeah. So we look back at the index 6 minus 3. Yeah. And we do a table here, dp, like defined like here, 1 plus the minimum of dp of 1 minus the c that we've picked. Yeah. And that gives you then the number 2 for the coins. Yeah. So you use the coin 3 2 times. Yeah. And we will I don't have the flow diagram, but we will explain it in the when we code it. Yeah. So how do you choose the right tool? Yeah. If you can divide in independent parts, you always try some divide and conquer strategy. Yeah. If you can make a greedy choice, yeah, for instance, if you want to find the shortest path on a map, that usually works, yeah, you use some kind of greedy algorithm. You find the optimal solution for one step, and the next step you find again the optimal solution and hope that it adds up. Yeah. If that is not possible, if they are not linearly independent, yeah, if the sub-problems overlap, then dynamic programming kicks in. Yeah. And that is very often the case, for instance, in optimization problems, in bioinformatics, and so on and so forth. There are lots of examples. Okay, so maybe to give it, to look at it, to remind you of the complexity. Yeah? So binary search was really a big improvement on linear search, yeah, because it makes it a complexity that goes from n to log n. Yeah? Merge sort was a classical divide and conquer algorithm. Yeah? And dynamic programming, we used it for problems where the sub-problems depend on each other. Yeah? And that also can help, again, reducing something from exponential to polynomial to n log n. Yeah? So that is a big advantage. Yeah? Okay, and that's the generic part. Yeah, now we have only 40 minutes until lunchtime. Do you have any preference? Yeah. Remind me, what can we offer? We can offer the binary search. Yeah. The merge sort or the coin problem. That's also nice. Should we start with the binary search to warm up, and then we can see how it goes, and we can do either the coin search, the coin change, or the other one. Yeah. No, Fibonacci we have to do. Sorry, that's very important. Maybe let's start. Sorry. I forgot about that. Let's start with Fibonacci. Oh, no. No, that's an example of dynamic programming. Let's do the binary search first, yeah, and then Fibonacci. So let's focus on the binary search now, yeah. And Deepika will give us some hints on where to start, and then we do the example of dynamic programming, so that calculating the Fibonacci series. Are there any questions so far? In lack, I can quickly check. Yeah, we will share the notes. Okay, perfect. Let's start with binary and then.
Okay, so we'll start with binary search in our Jupyter notebook. So an easy way to find it is actually to go to the content and then click binary search, and it should redirect you to the beginning of that section. Okay, so you can see I put up the skeleton for the binary search algorithm, and I gave a little bit of a hint that we need to use the variables left and right to indicate which part is the left side of our split array and which one is going to be the right side. So what this code basically means is the left is going to be defined as equal to 0 in the beginning, because on the left side, your indexing starts at 0. Arrays, you start counting from 0 and not 1. So, and then the right side will be the end of our array, which can be indexed, which can be worked out as the length of our array minus 1. Because again, we start indexing arrays at 0. So those are the variables you'll need. And maybe I'll give 5 minutes, see how far everyone goes. You can see here's basically what our main function would have been. That has our array, has our target, and uses our function. And I put a default return of -1, just to say in case the code does fail or doesn't find an element because it doesn't exist inside of the array, it will be element not found in array. Otherwise, it'll just show you the target. But you don't have to do that. You can also just return the answer. I shall put the pseudocode on the screen, because it's a very nice hint, and it's a very good way to learn how to program. It's to take your logic from your pseudocode and actually convert it into almost in any language. Pseudocode is just general. You can use it to guide you to write the same algorithm in Python, C, Java, almost any language. Here's a pseudocode. Hopefully that it guides you on how to build this function. Basically, we're splitting the array in two, and we're checking if this side, because the array is, it has to be in ascending order for binary to work. The computer automatically assumes, if your target value is smaller than the part in the 1/2, then it's going to discard that half, because in ascending order, it can't be there possibly, but it will be in the second half. And then you keep on splitting that second half until you identify where the number is located. That's why, fun fact, that's why it's called binary search. Binary as in two parts. That's why it keeps on splitting in two. Binary is also 0 and 1. Binary search will actually use a while loop because we want this loop to continue until we found our result. It doesn't have a definite end. So we're just going to say while the left side is smaller than equal to the right side. And then we have to calculate the middle, because what is the middle? Ah, what the double backslash does is just ensures that it's a whole number when you divide. So that gives you the position of where the middle is in your array. Yeah. Then we start with the conditional logic. And we want to be optimistic because efficiency in coding is key. So we want to assume, we're lucky, and by first chance, our middle is equal to our target value. Then we just return, and that's how the code can compile in a faster time, in optimal conditions, of course. So if the middle of our array, so that value, array middle means we're accessing that value that was positioned in the middle. And if it's equal to our target or the value that we want, then we return that value because we found it. That's best case scenario. Then we have two more cases. What if it's on the left half, or what if it's on the right half? Now we put another else if the middle of the array is smaller than the target, then we're going to have to get rid of the left side, because you can't go smaller and then find your number. We can only go higher. Say, for example, our number is 15, and then it can't be found in any of the numbers lower there, in that left half. Alternatively, you can also say if it's Else if it's larger than, and then you can discard the right half, but it's obviously your preference. Then we'll say your left side is going to equal to your middle plus 1. That's just getting rid of your left side now. Else the right side equal middle minus 1. Otherwise you get rid of your right side, depending on where your number is located, what your number is in this array. And then because this you want to account for all possible scenarios in this code, what if somebody puts in a value that's not in the array? Then you need some like way to exit this loop. Otherwise it can carry on forever, replenish your RAM. So you're going to have a return -1. Just if it doesn't meet any of these conditions. And then your array should be initialized. You can change your target to whatever you like in the array, maybe throw something that's not in the array. And then you can see our result variable is our function with the array and the target defined. And this condition basically says if the result is not equal to 1, not equal to -1, so again, our best case scenario is it is there, then it will print the sentence element found at the index. Else it will print element not found in the array. Compile this, you can press the compile. And it should work. Yeah, the list has to be sorted prior to actually using binary search, because we're splitting it in halves and assuming that this variable will not appear at all in this half that we discarded. And to assume that, we assume all the numbers are smaller than our target value or larger than. Please share the code. Okay. An interesting way to make sure that your array will always be sorted, you can use merge sort to actually sort that array into ascending order. Or Python has a built-in function that's just called sort. Sort array, and it should sort it into ascending order. Oh, I don't have the import. Besides working with numbers, when can binary search be useful? That is actually the next exercise. So in this case, we use numbers, but I want everyone to have this little challenge. Can you make it work for the alphabet, A, B, C, D, E, F, G, H, I, J, K? Because in the real world, binary search is actually used, you can even use it with ASCII characters which is a combination of letters and numbers. and special symbols, characters. And I'll give you a hint. You don't have to change your binary search function at all. It has something to do with your main function that you need to change in order to make it work for the alphabet. I'll give everyone a few minutes. Okay, so after some time, I think I've seen in the Slack channel, the solution is there. That's the right logic. You just have to complete the rest of the alphabet. So lucky for me, I'm just going to copy paste from my solution. Yes, you will have to, A, B. You basically have to make an array of the alphabet. That's the easiest solution in this situation. And then you just have to change your target into a string as well. So let's say we're looking for the letter F. And it should run. Element F found at index 5. 0, 1, 2, 3, 4, 5. Is correct. Okay, I hope everyone's happy and had that solution. Yeah. You basically just have to, the logic is the same. It's just the actual type needs to be changed, the variable type from integer to a string. And then while we still have some time, we will start with Fibonacci, and then we will have a break. Everyone's on the same page. We're going to continue. As Prof mentioned earlier, Fibonacci is a recursive function, and it uses dynamic programming, so a top-down dynamic programming approach, which uses cache. And cache is basically, I think you've heard the term before, maybe when they say you have to cache in computing, caching the registers. It just means storing the memory, storing pieces of information into memory. And what we want to do is we want to store the second last term and the last term in order to calculate the next term. And that's what the Fibonacci sequence is about. So to start it off, we're going to say if cache is none. What that basically means is that's how we're going to start our function. If there's nothing there, it means we haven't started the sequence. Now we begin with the logic. So the way the Fibonacci sequence starts is 0, 1, 1, 2. So the first term will be 0, second term will be 1, fifth term will be 5. So 0, 1 is 0 and 1. So these first two terms, they are set. So we only really start capturing the last two values after the second term. Hence why we say if n for the number of terms is larger than 2, smaller than 2, we return n. Because it will always be 1 or 0. Then we say if n is in our cache memory, we return our cache n. Cache That basically means if we already calculated it and it's in our memory, so say we already calculated Fibonacci of the fifth term, and it already has it in memory, it'll just pull that from memory instead of calculating it again and wasting computer power resources, which doesn't seem like a big issue now, but on bigger problems, you want to be fast. But now we do the calculation. If we do not have it in cache, we have to actually calculate the value using the two previous values. And how we do that is recursively. So we actually call the Fibonacci sequence within itself. And that's what recursive programming is, as Prof mentioned. So n minus 1 means the term before. And now cache. And then you add it to the second previous term, which is n minus 2. What that does is it loops back to the beginning of our function, and it checks, is it 1 or 2, and it'll return a value. And if it's not, if it's in cache, then it'll find the value, and eventually you'll get your desired final value. And then just to finish that function, return cache in. And to just check, always remember to run your code. There we go. Always remember to run your function before you run your main function. That's sequential order. Hopefully quantum computers will not have to do sequential coding. There we go. That's the dynamic programming approach for Fibonacci sequence. Any questions? Everyone happy? Yes. It is, I think recursion is one of the more difficult concepts in computer science theory. And yeah. So yeah. Is it better to write it so that the human understands it? I think at this level, write what you're comfortable with. Of course, on a large scale, if you had to use this for maybe an industry problem, then use this approach because it is proven to be more effective time-wise. Because the last thing you want is maybe computing for an hour when you can do it in 2 minutes. But yeah, do what you're most comfortable with. This is just a method. Yeah.
step is to get something that works.
Yeah.
And think about programming
That's,
in
yeah.
a fashion way. How can you record every time recalculate everything? Works.
That's computational thinking. It's finding a solution and then using abstraction to get rid of all the unnecessary things and then keep on optimizing and optimizing until you reach peak efficiency. Yeah.
That's a way to make it faster.
Yeah.
Safe. Hard to resolve.
But I promise it does come naturally after some time to think recursively. Yeah. Like we're currently running it on Google Colab. So it's using cloud memory instead of my actual computer RAM. You don't hear anything overheating. But back in the day, if you ran it on a PC, you have to use Okay, let's check this question. Yeah.
Here, enjoy the lunch break.
Yeah.
Until 1:30. Then we start. So I don't remember what we do after lunch. So yeah, then we will do a little bit of modeling. Yeah, so that very excellent. Then enjoy your lunch.
We'll see you.
At 1:30.
Yeah.
Yeah, so that's the plan.
Thank you.
Deepika, I think we've got like 3 minutes before break, so I would suggest maybe we break and then we continue after lunch. Can you hear me?
Hi, Krishna. Yeah, we will take a break here, and then we'll
Okay,
start
great.
after lunch.
Right, so at 1:30 we will continue, everyone. So we will see you all then. Enjoy your lunch.
Enjoy lunch, everybody. Thank you.
Okay, it is now 1:30. I hope everybody's enjoyed their lunch. Are we ready to continue? Deepika?
We are ready here as well. And before we start with part 3, Krishna, I think we will address a few of the Fibonacci questions that we had.
Yeah, sure. For sure, Prof. Thanks.
Okay, here we go.
Okay, I hope everyone had a lovely lunch. Just a little while to take a break, have a snack. Everyone's refreshed. So there were a lot of questions on Slack about the Fibonacci recursive and memorization. So using AI, we just built a little visual model of how this program is actually working, because visualization is, I think, one of the key parts in how to understand code. So I hope everyone can see my screen. Yeah. So this is going to visualize how the Fibonacci of 6 terms is going to work. If we look at it, it's computing 5, 4, 3, 2, 1. Then why this is so quick is because it's actually recursively going through the program and then caching, and completing. And then you can see over here, this is actually the values that were cached in our cache element that we defined earlier on in our notebook. And what makes it easier is just that you don't have to keep on going back and recalculating. It takes out all, it uses the principle of abstraction. It takes out all the unnecessary calculations in order to make this quick. I can replay it if everyone wants. 7. And just so you see, yellow is computing, because we have to get the previous terms, and then it's showing you in real time how it's being completed, what's being cached. And that is our final value, Fibonacci 7, which is a value of 13. We can actually check that in our notebook to see if we correct. Five, 6, 7. And there we go. It matches. So yeah, what recursion is, it's like doing a task over and over again, but instead of doing it by yourself, say we want to move 20 dominoes from one side to the other, instead of having one person do it, have 2 people doing it at the same time. That's what recursion basically is.
There are no more urgent questions. Proceed with part 3. Okay, part 3 will be about modeling. Yeah, and most of you will have to model something sometimes in your career. Yeah, and again, as quickly outline of what we will do in the next until 3, an hour and a half or so. Yeah, this will be a very nice example of abstraction. Yeah, then we will discuss a little bit modeling, discuss in detail a simple model for population growth. Yeah. And then we will couple it to how to extract the parameters for the model that you want to analyze. Yeah, so that will be very useful, and then we conclude with a summary, and we will spend some time programming our simple population model growth, and maybe also fitting the parameters afterwards. Yeah, so as I mentioned at the very beginning, yeah, when you start planning to model something, yeah, it's always important to think what is what is noise and what is essential. Yeah, so you want to remove all the details that are not really important and focus really on the characteristic aspects of your problem. Yeah, and that is, that's a little bit of an art. Yeah, because nobody told you at the beginning what is critical and what is not. Yeah, you need maybe to play around a little bit. Yeah. For instance, I mentioned at the beginning the example of the city map. Yeah, you don't want to know how many windows there are in a building if you want to go from A to B. Yeah, that's not really important. Anyway, so there are a few steps that we need maybe to discuss. Yeah, one is the concept of data abstraction. Yeah, so you're really interested in how the various data types behave, how they're implemented behind the scenes. Nobody really care. Yeah, for instance, we used before lists. Yeah, you just know the command list and how it works, but how it is linked in the machinery of your computer doesn't really matter. Yeah, and the same is happens now in modeling. Yeah, you want to use a function. Yeah, for instance, you want to take the square root of something. You don't care about the algorithm that Python uses to calculate the square root of the function. Yeah, you focus on you want your square root and you want to use it. Yeah. So in Python, yeah, you see the kind of the interface in your Jupyter notebook. Yeah, your various command, append, sort, list, or whatever, or length, or so on and so forth. Yeah, but you don't need to know how it's stored in the memory and so on and so forth. Yeah, all this is things that are kind of encapsulated in the black box that you don't care of. Yeah, essentially the same happens when you model the world. Yeah, this guy George Box, a statistician, he said this famous phrase that all models are wrong, but some are useful. Yeah, yeah. The perfect model probably doesn't exist. Yeah, models are always some simplified version of the world. Yeah, but if they help us predict the weather, yeah, that's fine. Yeah? But there is not a perfect weather forecast model. Yeah, there are good ones and not so good ones. Yeah? But they're nevertheless useful. Yeah? So don't forget that all models are wrong. Yeah. So the process is not perfect. Yeah. You start with, like, think of weather forecast. Yeah. You create your abstract model. Yeah. Then you need to put it on a computer to discretize the time evolution. Yeah. You simulate. Yeah. Then you check with the data. Was it good? Was it bad? Maybe it was not so good. And then you start again. Yeah. You make it a little bit better. Yeah. It could be that, in your first attempt, you neglected an important variable. Yeah. And it works only in some cases, but then all of a sudden it doesn't work. Yeah. So you make it iteratively more complicated. Yeah. Yeah, and the same we will do now with the population dynamics. Yeah. So a very simple model of population dynamic would be something like this. Yeah. The change in your population is proportional to the population with some constant. Yeah, which could be something the reproduction rate of whatever animals you're looking at. Yeah. Yeah. Those of you that know a little bit of analysis, what is the solution of this equation? Yeah, it's exponential. Yeah, and so it's written there. Yeah, so it's not such a good model of a population dynamics. Yeah, because it keeps increasing. Yeah, and yeah, and in every ecosystem, yeah, there is always a limit of how much you can increase. I think, for instance, if you have to model a population of lions in in the Kruger, yeah, at some stage they've eaten all the antelopes, yeah, and then they start dying because there's nothing more to eat. Yeah, so that's why a more reasonable population dynamic model, yeah, is taking this and subtracting something, yeah, with a certain rate. Yeah, that in some context they call it the carrying capacity. Yeah, how much food is there for the population to survive? Yeah, when the food is eaten up, you know, they start starving, and the population goes down. Yeah. So, and in this case, it reaches some maximal level. Yeah, there is some kind of equilibrium if you want. Yeah, so the more the population reaches this K, the less the growth is. Yeah, it's starting slowing down. Yeah, so this is a more realistic model. Yeah. So if you were to compute it, which we will do just now, yeah, you see this is the value of the K. It starts increasing very quickly, but then the second term with minus P over K kicks in, and it reaches some kind of asymptotic scale. Yeah, instead of continuing to grow exponentially forever. Yeah, and this is a typical S-shaped curve that some people also call logistic growth. Yeah. Okay, so the question is now, how do we calculate this? Yeah, how do we bring this on the computer? Yeah. And if you look again at the left-hand side of the equation, dp over dt is the rate of change. It's essentially the slope at various moments in time. Yeah. So when you simulate it, you don't simulate it continuous in time. You need to introduce discrete time steps. Like here, you calculate from here, you calculate the slope here, you multiply it by a time step, you reach here, and then you do the same and the same and the same. Yeah. So at each time step, you calculate the slope, and then you move a short distance proportional to dt in that direction. Yeah, that's what you do. And the most simple such algorithm is called the Euler algorithm, yeah? Which is essentially in mathematical, if you have a function like this, think of y as dp dt is equal to something. Yeah? So you discretize in equal time steps of width h, yeah, and you calculate the new time n+1 from the old one plus a small number, the time step, times the slope of the function. Yeah. For our example, yeah, remember this was the equation. Yeah, in continuous variables. Yeah, that was the equation. If you discretize it, yeah, with this very simple Euler algorithm, it becomes something like this. Yeah, the population at time t+1 is the population at times t plus a small time step times r times p at position t times 1 minus p at position t over k. Yeah, and delta t, you know, should be chosen small. Yeah, which for practical purposes could be something like 0.01 or something like that. Yeah, that if the p's are of the order of magnitude 1 or so. Yeah, so it should be a little bit smaller. Yeah. Okay. So there are, of course, this is the simplest algorithm to integrate such differential equations. There are many others, yeah? But for our purposes, it will do the trick. Yeah. But the important thing to remember is just the time discretization, yeah, and the time step. Yeah, that's very important. Yeah. Now, if we go back, to our model here, yeah, you see there are two parameters. Yeah, there's R and K. Yeah, and when I did this plot, I just chose something. Yeah, but if you want to your model to be a good model, let's say for a population of elephants in the Kruger, yeah, you need to have a system to estimate out of data that you have R and K. Yeah, you need to collect data, and from the data, you need to be able to extract R and K so that you can feed them in the model and see what happens in future. Yeah, and this leads us to the next important concept, which is parameter estimation. Yeah. So the model has two unknowns, yeah? Two unknown parameters, R and K. Yeah? How do we find them? Yeah? The simplest way, and there are, again, many methods, yeah? Is least squared method. Yeah? You have your data, yeah? Y and F, yeah? And you sum in your discretized fashion, yeah, the square of the difference. You square the difference, you take the difference of your estimated values and you square it. Yeah. So you look at the difference between the prediction and the actual data. Yeah. And you minimize it, and out of the minimization, you extract R and K. Yeah. And for some, in Python, in SciPy, there are lots of packages, curve fit, and so on and so forth. You just type it in and it comes out. Yeah, but maybe we can do the least square model by hand. Yeah, so the idea is you take the difference of the observed data and the predicted data. Yeah, like here. This is your model, and these are your predicted data. Yeah. You take the difference, you sum it, and you minimize it. Yeah. There are technical assumptions that go into this. Yeah, that everything is Gaussian and so on and so forth. Yeah, which might be the case or might not be the case. Yeah. For instance, this minimization procedure, if the data are linear, you can essentially do it by hand. Yeah. But this is a little bit more non-linear, yeah. So you really need to do it numerically, yeah. And as I said, there are Python packages like this one here that do it for you, yeah. I don't want now to go into the theory of nonlinear optimization and things like that, but you just need to know what package to look for, and it works. Yeah. Okay. So this is how we would look like for your population of I don't know, of elephants. Yeah. Yeah. You have your your data points, and you want to fit a logistic curve with your and you extract from the fit your parameters K and R. Yeah. That's the basic idea. Yeah. So I mentioned, all models are wrong, but some are useful. Yeah, you probably have the high school physics example of throwing a cannonball. Yeah, and ideally it's a parabola. Yeah, but in real life there is air resistance. Yeah. that causes friction. So in real life, it's not a parabola. Yeah? So you need to add, if you are in the military business of cannonballs and you want to be precise, yeah, wind speed, humidity, everything plays a role, yeah, and you need to feed it into your model to do the prediction of the trajectory of your cannonball. I mean, you could do it with basketball; it's probably the same, yeah, probably less dramatic, yeah. So it depends what kind of level of description you want, how detailed you are, yeah. So again, before we start computing, yeah, the important things to remember is essentially these two last points. Yeah? Once you have your model, yeah, and you're happy that it satisfies your need, yeah, you simulate it numerically. For instance, with Euler's method, that is very, very basic, but always works more or less. Yeah? Once you have that, you have a tool to compare your simulation with your data, which allows you to extract the right parameters for your model. Yeah? And those parameters you feed again in your numerical method and do a prediction. Yeah. So, and I think this is what we will do now. Yeah. We will try now to see that we can produce something like this. Yeah. By integrating the population dynamics for the logistic growth. Yeah? And you're welcome to first start with this. Yeah? Just do the exponential one. When that works and that explodes, yeah, you can fix it by introducing a correction term that slows the population dynamics. Yeah? And since we have about an hour, we should have enough time to do the fitting of the parameters as well. Yeah, so that you see how, at least in principle, how to apply it in a real life situation. And maybe as a last comment, this is how we used to do it. Yeah. In the meantime, there are super efficient AI tools to do these kind of things much better, much faster. But that, since you have machine learning only from tomorrow, the machine learning part. Yeah? Maybe at the end of that, someone will show you how to do it in that way. Yeah. Okay, Deepika, now over to you.
Okay, thank you, Prof. As Prof mentioned, we're going to start with the logistical growth model first, and then once we get that logic down, then you can apply a fitted curve, a curve. In our workbooks, there should be a logistic growth section. And the imports are there, but you can run it quickly just to make sure that they work. That means if you're using Anaconda or VS Code or another platform, you'd have to install it using maybe a pip module. Just put in pip install matplotlib. So because this is a formula that Prof explained before, I've put down the parameters of the variables you need to initialize and what the type of the variable is. So float, in this case, all of them are float except for your steps, which is going to be an integer because you want it to be a whole number. So how about we have a little challenge and see who can make this formula, this logistic growth discrete formula, and then return the result, which would be the population. Yeah. And I'll put up the formula on the board. Give everyone 5 minutes. As a hint, you will have to use a for loop. Anyone successful? Okay. So we can start by making a variable p equal to the initial population. Then we want an array to store all of our population values over time. So we're going to say populations. Equal to a list of p for now. Then we start our for loop. You can say for I or whatever you like. You can even use a underscore if you don't want to have a specific variable just for your loop iterations. But I like using I. And we say in range steps because we are going to go according to steps as said by the formula. And as you can see, steps is the number of steps to simulate, or as it usually is, the change in time. So we're going to say dp, which is the change in population, is equal to r multiplied by p multiplied by 1 minus p over our capacity times the change in time. Which, if we go back to the equation, you can see it's just rearranged in a way to get the population. That's one single value. And we want to append it to our array populations. So how do we do that? We do that by appending, using the append function. And yes, it's a little bit mathematically complex, but as you can see, it's only a few lines of code. And that's usually how modeling ends up. You have this huge problem, and it only ends up being 2 or 3 lines of code. And of course, we return our value populations. Now, in order to graph this, we have to set our parameters. So, as Prof said, we have this carrying capacity of when the food runs out for the lions. And we just set that to 100. But now, let's say my steps are equal to 10. So my time period is 10. We run this. Then you can see this graph is linear. Everyone's familiar with pie plot? Yes, okay. What this population values is it takes our function and then it plots it onto this graph. And we can play around with the values. See, as you add more steps, you can see it starts to curve. And then it plateaus. Oh, yeah. So let's change the value of the carrying capacity to 0 and see what happens. Of course, it's going to be not going to compile because it's going to be undefined. 2.5. That's the interesting thing. Play around with your values, get different graphs, get different models. And using your data sets in research, important to look at the different combinations and variations in order to see which parameters fit your real life values perfectly. Change the R. Then you see the change in the rates is much more, has increased exponentially. To see it closer up, we can change the steps to maybe 10. And there we go. Now that you have the basic understanding of how to use the formula for logistic growth, the next step would be to look at logistic fit. It's to see how your data values actually fit a curve. Okay. If anyone hasn't logged their attendance today, please do. If you play around with this code, you can see the individual data points compared to the logistic curve. And what's interesting, as you can see, there are some outliers and others fit the curve. So this uses least squares adjustment method. Yeah. That's just from running the code, yeah. Yeah. The real challenge for the rest of, until somebody figures it out, hopefully, would be to build your own population model. Of course, it's a big job as beginners and intermediates, but following this skeleton and using the code from the previous exercises, you should have an idea of how to build it. Using the same formula, the discrete logic growth, as you can see, it has the same parameters: initial population, the R constant, the carrying capacity, time difference, and our steps. And this model is actually a little bit more realistic. It takes into account the mean, for example, which you'll have to calculate using the mean formula. Yeah? Make it less daunting. The only functions that have to be completed is discrete logistic growth, logistic continuous, and your mean. Yeah. Is that a fair task? Yeah. You can use the resources in the document because that will definitely help you. And I'll walk around and love to see how everybody's models are coming together. But to note, one of the computational thinking pillars that are used in this population growth model is abstraction, because of course we don't take into account the age of people in this population, in the sample population. We don't take into account environmental effects, maybe natural disasters that could cause a decrease or a spike in population. Like if you look at the population graphs provided these days, you'll see in 2020 due to COVID, there is a drop indicating the epidemic. And that's one of the trends that you can observe.
Deepika, can you hear me? Can you hear me in Stellenbosch?
Can hear you.
Yes, so it seems the participants are really not sure of what to do now. So maybe can we go over what they need to do one more time?
There's two functions that we have. There's two functions that we have: discrete logistic growth, which we covered both theoretically and practically in our Jupyter notebook. So not to point it out too much, but if we look at the logistic growth.py document, we'll see how we coded together using the formula, and we returned the populations value. And that's basically our data set using all the parameters. And what we want to do now is take these data points and then you also use logistic fit, merge them together and create a population model. And as you can see, there is also comment in logistic growth continuous that kind of guides us on how to code this function. I hope that's clear. Thank you. It's just as I repeat, the two top functions. And then of course, calculating the mean, which is something we do in high school when we take the sum of all the values and then how many values there are. We divide them by each other to get the mean value. the average. Work together, we can calculate the mean. And say the mean is equal to going to be the sum of our values. The sum function will automatically add up all of our values. And then the length of our values, which tells us how many values there are. What we can do is just return that. That's the mean. So the main function uses plot. It's going to plot our graph of all of our points along a curve of what this population model is going to look like over a time period that we defined as 100 steps. And then we have a growth rate of 30%, which is fair. Of course, our initial population is very small, but this is for science sake. As you can see, it notes that, like I mentioned, abstraction is used in this model. Takes out the factors of spatial distribution, is population per unit area, and predator-prey interactions if possibly someone got eaten by a shark. For discrete logistic growth, our code is actually exactly the same as our logistical growth function. So you can copy and paste if you'd like, or write it out together. Start again, populations is our array is equal to the initial population. Just make sure it matches up with our defined variables in the function. Now for our loop. Once again, the end of our loop is going to be defined by steps. And we use the discrete logistic equation, which is change in population equal to R times E multiplied by the change in time, which if we go back to logistic growth, is exactly what we did. We're just not appending it yet. The only difference is that over here, the parameters or the variables are just in lowercase. Now what we want to do is add the change in population to our population and then append this to our array so that we'll be able to display every individual point. To ensure continuous logistic growth, we can start with defining that the initial population is not allowed to be smaller than or equal to 0 because that's just not possible. And if it is in the case, then we'll return 0 to indicate that there's an error. Otherwise, we'll continue with defining our factor from the equation, which is going to be part here. Minus the initial population divided by the initial population. I think you're all wondering maybe, why did we import math? We didn't import it for nothing. It was to use the exponent function or expression. So we're going to return our value of our equation, which is k So the math.exp basically means we're accessing the maths module and getting the exponential function from it instead of having to write to the power. And that's going to be r times t. Yeah.
There is a question on Slack.
Yeah. So is the population factor k same as the constant from the exponential? Is it just any constant k of or population factor? In this case, because it is a population model, it is going to be a constant population factor. But in any other model, it will be any other constant that is in relation to what we're calculating. Maybe for the rate of resistors on a CPU, I share the code. That graph would be the constant for We have an indentation error. There's an indentation error somewhere. Yeah. If anyone finds this indentation error, it will be the master code of the day. Yeah. Yes. It is. It's a fail-safe, yeah. I will. Not necessarily, no. Because an array can be still be undefined or empty, or which is why that in this case it is slightly paranoia, so you might not need it, but yeah. 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 It can be a bool or like true or false if it exists or not, yeah. Okay, with the amazing help of Gemini, we found our indentation error, which is which was actually the return populations was indented wrong. So that is one pro of using AI. It saves hours of debugging when you're tired and you overlook certain lines possibly, or you just have bad eyesight. So with that fixed, you should be able to run the code in the section, and then we get an interesting output. We get our simulation results. I hope everyone was able to run this code. Yeah. Okay, okay. So we start off our model with the discrete logistic growth, which we've discussed previously and used. What we did is we basically calculated the populations and put it into an array, which we then return properly after the for loop and not during the for loop with this corrected indentation. Then we look at the continuous growth, logistical, which we then discuss that we cannot have an initial population below 0. Why? Because it's not possible. And then as a failsafe, we return 0. That would basically stop the program from running and just give us an output of 0 so that we can track back and start debugging from there. But of course, because we're so talented, we didn't return a 0, and we went on to define our factor, which is k minus the initial population divided by initial population, as defined by our time, our population at that certain time. And then we returned the whole value, which was k plus 1 of the factor. To be honest, you can just do it all together. Instead of putting factor, you can just put in the whole formula as that. But then what makes it better to do it separately is actually bracket errors. So just like in mathematics, there's certain functions that you have to perform before you do others. The computer has to know when to do these calculations. So because we want to calculate this value before and not after, possibly to alter the final output, we just do it separately to be safe. But of course, if you do proper BODMAS, it should be all right. Python can handle these cases. And then what the continuous logistic growth function does is it takes the time and it makes these points that we will eventually, that we look at in our output. And then we have estimate growth parameters. So this uses linear regression, which is a very common regression model used in machine learning, which we'll cover in the next few days. And this is, of course, the simple version, as we're doing an abstract population model that eliminates things like disease, epidemic, things like that. And then we have our mean values, which we calculated by the sum divided by the total terms. And then we have our main method, which when run will give us a nice summary of our population growth model. Just stating our parameters in the beginning so that we can see what was changed when we play around with the values. And these are our simulation results. At time 0, the initial population was 10, and that's correct. And then at time 25, with our growth rate of 30% and a carrying capacity of 100, we have a population of 18.9. Of course, we can always round it up using the round function because I've never met a 0.9 of a person. But yeah, at time 100, we can see that the population is 68. Of course, in this simulation, time is a scale. It's not set like 1 year or 10 years. Of course, you will then adjust this to your data. But in this instance, we can look at it as simulation steps. Instead of saying days, it could have been years or maybe months. And then there's just a little bit summary of what it abstracts away and the parameter estimations. Yeah. Basically. The projection, yeah. We're not using real data. We are. That's exactly it. Because we're generating our data, obviously it's quite, how do I say, optimistic, quite optimistic data. So we do use a simple linear regression model. Of course, later in the week, you'll realize how to fit a regression model to live captured data. Yeah. Yeah. Yeah.
Just have to show you the basics.
Just the basics.
Yes. Really do the basics. Have a sort of foundation.
Build on it.
Trying to ask this. So that's why I told it.
Is there any question? Is a lot of content pieced together.
This is separate. Then
Put it all together.
Put it all together. Yeah? That's how it works in real. Works in other piece. I think it's
our detail.
1 minute to 3 or 2.
Two.
Let's stop here. Yeah, and 3, the last sprint. So, thank you very much. Okay, we are ready to go. Okay, we have a few seconds. Krishna, is everybody ready to go? I can see that we're on the last stretch because the number of participants, okay, it's picking up again, was decreasing. We can do the time series analysis. Okay, it's 1:15 now. Let's start for the last stretch. We have only 45 minutes, so it won't be too painful. Yeah. And in this last section, sorry, I need to put it here. Oops. Okay, I wanted maybe to mention just a few things. Yeah? Say a few words on pattern recognition, yeah, without going into too much detail. Summarizing a few of the things that we said before and encountered before about the complexity analysis, just that you get used to a few buzzwords that come up in that context. Then I want to address a little bit the standard topics in using graphs, yeah, because graphs are a very useful tool that occurs in many branches of science, and yeah. Then we have options. Yeah, here we have one example of campus navigation. Yeah, because we thought with Deepika that instead of doing a quiz, we give you an assignment. Yeah, and we have a few options. One is this one here of campus navigation that maybe Deepika can share at the end something. If not, we could do the coin change problem that I mentioned, but that we didn't do. Yeah, or that we have on sale. Okay, those are probably two options, and some of you can choose the one, some of you can choose the others. We are very flexible on that. Yeah? Okay, so on pattern recognition, yeah, it's always useful, yeah, to find recurrent patterns. Yeah? For instance, one typical example that we could discuss also as an assignment, yeah, is we could give you a time series data, yeah, could be the rainfall in Stellenbosch or sunshine in Mpumalanga, or something like that, yeah. And you should try to analyze the pattern in those data, yeah. There will be seasonal patterns, yeah. For instance, in Stellenbosch, it rains in winter and it doesn't rain in summer. So if you monitor the rainfall, you should pick that up, yeah, ideally, yeah. But maybe there are also long-term trends. Yeah? Does it rain more or less over the couple of last years? And are there anomalies? Yeah? A few years ago, we had floods in Stellenbosch. That was definitely an anomaly. Yeah? Something that doesn't happen every year or doesn't happen regularly. Yeah? And you can analyze those things by very basic statistical measures, yeah? By seeing how much something deviates from the mean, for instance, yeah? Just as an example. Yeah? For instance, this would be, you could make it a little bit more fancy, detecting anomalies in server traffic. Yeah? Sometimes bad people attack servers, yeah, to shut them down, yeah. And then you can see, for instance, over time, there are so many requests, and all of a sudden, boom, it jumps by many orders of magnitude, yeah, and boom, and the system crashes. Yeah? That happened before, yeah. But the art is then to detecting that happens before it happens, before it's critical, yeah, so that you can make take the approximate, the necessary countermeasures. Yeah. So, so this is something that we could make as a simple assignment, yeah, instead of the quiz. Yeah. So the other thing that I mentioned a few times, in particular at the beginning with the search algorithms, yeah, is the complexity analysis. Yeah. You know, first step is always get something to work, yeah, and then you want to make it efficient. Yeah. And complexity analysis is the tool that allows you to formally analyze a code and show its complexity. Yeah? And there is this famous big O notation, yeah, that we that I sort of used before without mentioning it. Yeah? Remember, we had algorithms that were linear in complexity. So if the data set increased by n, increased linearly, the time it takes to find the entry in the database also increases linearly. Yeah? This would be the big O of n. Yeah? So the order in which the computing time, the complexity increases by increasing the typical parameter of the system is linear in the parameter of the system. Yeah? So this would be the O of n. Yeah? Another one that we encounter was the n log n. Remember, yeah, that would be this one here. Also not too bad. Yeah. If you start getting polynomial or even exponential, then it's very bad. Yeah. Because you see, if you double the size of your system, yeah, from here to here, it increases by more orders of magnitude the time it takes you to find a solution. Yeah? And if it is exponential, then it's really bad news. Yeah, yeah, or just increasing a little bit the complexity makes it exponentially longer to compute the running time. Yeah, so this is really very important when you look at algorithms. Yeah, try to get algorithms that are down here. Yeah, the ones that are exponentially in complexity, they're not so good. Huh? Okay, now just to give you an example, assume you have 10 to the 9 operations, yeah, and n is 100. Yeah. If it's linear, you can do it in nanoseconds. Yeah? If it's exponential, you need trillions of years. Yeah, so it goes up quite dramatically. Yeah, so 100 operations become 10,000, and exponentially 2 to the power of n is already 10 to the power of 30. Yeah, so it's really really takes a long time. Yeah. So in other words, if your algorithm is exponential, just going to incredible connection and buying a faster laptop doesn't really help. Yeah? You need to sit down and think of a better algorithm. Yeah? That usually helps. Yeah? Brute force doesn't always help. Yeah. Okay. Now, because we still need to practice a little bit, and maybe that's what we do. Yeah. Let's spend a few words on graphs. Yeah. Graphs, you all know, it's something that has a vertex and a node and an edge. Yeah. So you have nodes connected by edges. Yeah. So let's call V the vertices and E the edges that connect a pair of nodes. Yeah. And you know, we all know social networks. Yeah? Each of us is a vertex, and the edges are the connections. Yeah? I'm friend with Deepika, Deepika is friend with you, you're friend with the person behind you, and you build a graph of connection. Yeah? Other obvious graphs are transportation networks, yeah? Or the internet or whatever. Yeah? So there are infinitely many examples. Yeah? But let's, you know, the idea is to find a way to mathematically describe such a network. Yeah, could it be the subway system, could be I don't know, whatever other system. Yeah. And in some cases, the edges have certain weights. Yeah. For instance, you know that to go from C to B, if this is some subway system, yeah, takes 2 minutes, for instance. Yeah. But going from A to C takes 5 minutes. Yeah. Even if the distance is the same, let's say, but there is a difference in time. Yeah. So, and these are, if there is such a weight, one speaks of weighted graphs. Yeah, it's not just a matter of connecting the dots, but there is an additional weight to connecting the dots, yeah? And that makes a difference. Yeah, so we have unweighted graphs and we have weighted graphs. Yeah? So in unweighted graph, all edges are equal. Yeah? So if you need to find, typically if you have a more complex graph with, let's say, A, B, C, D, E, F, yeah, you want to know how easy is it to go from A to F? Yeah, what is the shortest route, for instance? Yeah, but if you have weighted graphs, yeah, you need to take into account that there is a cost to a different distance. Yeah, for instance, traffic. Yeah, to go from Stellenbosch to Somerset West at 5 o'clock takes longer than at 2 o'clock in the afternoon. Yeah, so that is a complication. Yeah, and there are two very famous algorithms. Yeah, one for unweighted graphs, which is called breadth-first search (BFS), and this is a very, very famous algorithm for weighted graphs to find sort of the easiest optimal connection between points. Yeah? And I want to briefly describe them because they're really very easy. Yeah? So the algorithm for non-weighted graphs, yeah, is you look at your graph sort of in layers, yeah, and then you check the distances from layer to layer, yeah, and all the weights are all the same. So you just need to find out to go from A to E. It's just 1, 2, 3, and you're there. Yeah, that's the shortest path, and you're guaranteed it. Yeah, to find it. Yeah, and we will program it just now. Yeah. This one is also very interesting. Yeah. This is essentially an example of a greedy algorithm. Yeah, in a weighted graph. Yeah. So how do you do it? Yeah, you start somewhere. Yeah, and you find the smallest distance to all neighboring nodes. Yeah, and then once you're there, I will show it you just now. Yeah, you do it again. Yeah, and then you relax a little bit. The connection to see if you can find a shorter distance, considering the weight. Yeah, and then you update, and then you repeat until you reach the destination. Yeah, and I think I have a yeah. Here we go. Yeah. So this is the idea of the relaxation. Yeah, you're here. And your weight from U to V, let's say, is 5. Yeah? Then you check whether the distance from U plus the weight to go from U to V is smaller than the distance to go to V. Yeah? If the answer is yes, then you know that the distance to V is your whatever it is, 10 plus 5. Yeah? If this was 10, then you need to add just the 5. Yeah. So it's essentially like the previous one, but with the complication of the weights. Yeah. and okay, should we discuss this at the end? Yeah, maybe it's better. Let's not overcomplicate things. Yeah. Okay. Yeah. Now, because we thought maybe this could be an example of assignment, but let's see how it goes with the two graph algorithms. Yeah. So I'll give them to you.
Good. So as Prof mentioned, there's two graph algorithms, one weighted, one unweighted. We'll start with the unweighted breadth first search, which searches through a graph horizontally. There's also depth first search, which goes vertically. So what breadth first search uses is a queue. And then what a queue does is there's two data types, a queue and a stack. A queue is like the lines we stand in. There's one comes in, one goes out. A stack is like when you take chips out of a container, like out of a Pringle container. You have to take one out and put one in from the same entrance. The queue flows faster than a stack, of course. Yes. Hope that is clear. So in breadth first search, we actually use queues. We put one value in, put one value out. So how we want to start off our function, as you can see, I have an example graph here of the graph that we're going to use. Now this is how we would lay it out to feed it into the program, where we define the point A, or like we say node. It joins to points B and C. And I don't know if you remember, we used the dictionary before. This is a dictionary as well, and it has, instead of one value, it's multiple values. So we have A, B, C, D, E, F. Those are our nodes. Of course, looking at this is a little bit confusing to us humans. So to visualize, this graph makes it a little bit easier. So we see A connects to B and C in the one direction. But then if we look at B, it also connects to A and it connects to D. But to confirm, D only connects to B. So we'll do a reciprocal diagram, which the computer will understand. Then E is connected to B and F, so reciprocal. And F is connected to C and E. So if we look at it, the only lone node would be D, which has one single connection. What we want to do now is we want to start by defining our variables. We want to start our queue, and we're going to say, okay, this queue is going to be set at a start value, and that start value is going to be the node that we give the program. And then visited is going to be like our queue is going to track which nodes we visited in the program. So for this, because we don't know when exactly we're going to find our most optimal path, we're going to have an indefinite loop. So we're going to say while queue, which basically means while there is a queue, while it is populated. So while there's a queue, queue.pop left, it means we're just traveling to the left. Then we index the path to just know where we are in our array. And then again, we're going to be optimistic and assume just by luck, the first try, our node is equal to our goal. So if node is equal to our goal, double equal for equates, then we want to return our path. And that's going to be our shortest path. So hooray, if it works, the code exits and you don't need any more logic. But of course, that's the best case scenario, which is almost never going to happen. So now we have to check all the neighbors. And what a neighbor is the nodes attaching to your start node. So we're going to have to put another loop within this while loop saying for the neighbors, for our neighbor in this graph, which was defined for our neighbors in our graph, we just want to get the node and then we want to perform an action to see if that node is the one that we need, if it's our goal. And basically, to find the most optimal path, it's inevitable that we have to visit every node. Because, you know, in these possibilities, you have to check everything out first to see which one is the most efficient. We say if neighbor not in visited, visited.add neighbor. Because we want to add it to our visited list to keep track of where we've been. Then we'll say our new path is equal to our list. And then we're going to add that to the path. Add our neighbor to the path. And then we added it to the list, but now we have to add it to the queue as well. So we're just going to queue dot append I have seen people code this using arrays, but which is a bit more difficult. But using queues is the proper data structure. But if anyone tried to attempt to do it with an array, that's perfectly fine in this scenario. Now, of course, because this is a while loop, it's going to run forever. And if we input data that's not part of our graph, it's just going to keep on going and never return. So we just put a return none. That just means, you know, nothing was found. Okay. So here's our graph. We can use it to double check our logic, because we can't just trust what we've done on the first try. First, let's run this code. Compiled. And then, as you can see, the graph has been defined. The start node is defined as A. The goal node or the end node is F. And then we used our function here. Then again, there's an if statement that says if there's a part, else if there's no part, depending on if it's returned none, which isn't necessary, but it's just there. Let's run this code. Oh, let's run the imports first. That's the nice thing about Colab is you don't have to take 10 minutes just to find all the imports and then worry about which environment it was installed into and move it over. It's already in our notebook. So there, our output says the shortest path from A to F is A to C to F. Now, I don't trust the computer, so let's check. A, you can go to C, you can go to F. There's only 2 steps. I go to C, I go to F. If I check the other route to B, then I have to go to E, and then only I get to F. So yeah, it is the most optimal route in the end. Any questions?
There are no questions on Slack, but there's a request to please zoom in. They can't see.
Okay, thank
Oh,
you.
yeah, there's a question now. Sorry. Do nodes have to be bidirectional? That's the question.
Nodes has to be bidirectional. No, they do not. They don't. For example, okay, there's no example here, but no, they do not. Answering your question, array. A queue is just a faster data structure to be able to store this this logic, because a queue allows us to put in and take out and pop. And pop is a very essential thing in graphs, because we want to remove things, but if you had an array, you'd have to explicitly go to the specific index and remove it, rather than if you say pop, it just takes the first one off. Again, this is a very basic implementation, so it may seem unnecessary in this case, but trust, in larger applications, every second counts. I'll just yeah. That is true. It's important to know your imports, because these are tools that are freely available, and it makes your life just 100 times easier compared to, for example, in C, which we had to build these data structures from scratch and make the memory allocations manually. It's just a pain. Python is lovely. There's no segmentation faults or anything. In a practical workplace environment, where would I need to apply BFS? BFS is actually maybe not in the workplace environment, but definitely applications like Google Maps, where you need to find the shortest route. They actually use Dijkstra's, which is the weighted version of BFS, so it's breadth first. Otherwise, more commonly used is depth first search, which is you first go horizontally and check all the nodes until you find the largest distance. And that's used for also map applications. I do know, however, in banks they do track clients' transactions and maybe accounts. So like if you have a person's profile, they can use depth and breadth first to actually track how many accounts do you have, how many transactions you made, and it just branches off. Even in police data, if you have a criminal record or something, everything interconnects using this graph because it just maps through your name. Even your ID number. You just need a common field to map through. Well, everyone's happy with the breadth first search. Do these path algorithms apply to the hidden Markov modeling that's used a lot in bioinformatics? I assume so, but the Markov model is a bit more advanced. While I'm copying and pasting, if anyone wants to attempt Dijkstra's algorithm, which is the weighted version of BFS, the only difference would be that instead of having your loop where it loops through your nodes, you have to add distance in there somewhere so that it also realizes the distances and not just the graph. As you can see, we also use nodes here. This float, INF, stands for infinity. As you can see, the example is I use in South Africa, I have a dictionary that says Johannesburg, Pretoria is 50 kilometers away, Soweto is 30 kilometers away. I hope someone fact checks me, but this is assumptions. Pretoria, Johannesburg is 50, Bronkhorstspruit is 60, Soweto, Johannes, and then you see that's our dictionary. And if we look at our BFS, it was very similar to that. It just didn't have the distance. Where is BFS? It was identical. It just had this one value. Whereas in Dijkstra, we have the value and we have a distance, an integer. So we're almost done. Let's code our while loop. So the reason I gave the while loop in this template is because we covered it in BFS. So that logic should be fresh in your mind. And now we want to say if our node is not visited like we did last time, we say if the current node that we're at is none, or the distance, because now we have to factor in distance, is smaller than the distance of the current, so if you think back to when we did binary sort, we had to see which one was smaller, because the smaller one, according to what we needed, is what, and in this case, we want the least distance. So of course, we're going to put smaller than. So if the distance of the node is smaller than the current, then we want the current to switch over to that smaller value. So then we'll have to redefine current as that node. We just reinitializing, weighting it. And then I hope everyone understands we're going to indent in line with the for loop, because we haven't broken the while loop yet, but we're still in it. We're going to say if current is none, or the distances of the current is infinite. So these are our fail cases for Dijkstra's algorithm. Obviously, if the distance is infinite, that's definitely not our most optimal path. Then we want to break the program. So we'll just stop the compilation, or like once again break the while loop so it doesn't run on forever. Then we can say visited dot add current identical to BFS. And then now that we've covered the node visiting logic, we have to somehow connect the node and the distance together in a loop. So for neighbor and the distance, because in our dictionary it is a tuple. Tuple means like more than one value. In our graph, are our current item, so we're accessing. We're going to say our new distance is equal to our current distance plus distance. And that's basically what our result is going to be. If new distance is smaller than the neighbor's distance, then we're just going to make the distance equal, the neighbor distance equal the distance, the new distance. All right. And then return distances. Compiled. It didn't compile. I will admit, when I practiced this, I had a similar error because I spelled neighbor wrong. So just check your spelling in these situations. New distance. Distance. It is not associated with a value. Could be an indentation error again because
I think someone found the issue. Check Slack.
not distance. Which I defined in the start as distance. Yeah. I understand what you're saying. Okay. Let's just accept that. I don't know what that did. Distances. Distances. This is a counter, so it should be distance. Maybe this is, no. My professor once told me if it works, don't touch it. And magic can happen in computer science. Okay, well, let's just check this logic. If we start from Johannesburg, Johannesburg is obviously 0 kilometers away. That's great. Pretoria, 50 Ks. Okay, yeah. So where to 30 Ks. And then Bronkhorstspruit, 110 Ks. And that's correct, because if you add it up, Joburg, and the shortest path, Pretoria, Soweto, yeah. I hope that makes sense. It's incredibly famous, yeah. It's been around for maybe like, yeah. It's one of the first algorithms, and like I said, if it works, don't touch it. Yeah. It's actually the algorithm they use in Google Maps. Obviously a little bit more advanced, but this is the basic logic, yeah. Yeah. Of course, yeah.
It's almost 4.
Hope,
It was useful.
hope everyone learned something
Yeah,
today.
at least a little bit. We will see you at least the Bush guy.
Yeah.
So, and also, good evening to everybody out there that we
Yeah.
don't see. Yeah. Thank you for being with us again. Participant in this morning, so that's probably a good sign. Yeah. Yeah, I hope everybody clicked their attendance thing. It did. Perfect. We meet again tomorrow morning, same place, same time. Yeah. So have a good evening, everyone. Thank you.
Thank you.
Everyone. Yep.
Thank you, Prof. Thank you, Deepika. Thank you to everyone at all the different venues. So yeah, we start again tomorrow, 9:30.
Excellent. Thank you. Thank you, Dr. Kila. Bye.
Bye.
Bye.